Here I've got two problems from the Pan-African Math Olympiad. One comes from the year 2009 and the other from the year 2001. So let's jump right into this first one. And it asks the following question. Can we find x1, x2, x3, all the way up to x 2009? So in other words, we've got this sequence from the set -1 to 1, such that x1 times x2 plus x2 times x3 plus x3 times x4 all the way up to x 2009 times x1 equals 999. And the way this is phrased, you should probably guess that the answer is no. And that's because it's asking if something is possible instead of asking to find all examples of such a thing. And furthermore, since there are so many moving parts here, finding an example would be tricky, and finding all examples would probably also be quite a lot trickier. Okay, so we're thinking that the answer to this is no, so let's get down to showing that. And so we'll do that by way of contradiction. So by way of contradiction, let's suppose that x1, x2, all the way up to x 2009 come from the set plus minus 1, just like our setup, and they satisfy this equation. So x1, x2 plus x2, x3 plus ... plus x 2008 times x 2009. So I'll insert one more term here, plus x 2009 x1 equals 999. So let's notice that we're adding up a bunch of numbers, 2009 numbers in fact, that are all either 1 or -1. So they're 1 if the signs are the same, and they're -1 if the signs are different. So just by counting this up, what we see is of these summands, we know exactly 1,504 are equal to +1, and then the remaining are equal to -1. So that'll be 505 are equal to -1. But if we have 1,504 ones and 505 minus ones, that means if we take their product, we'll get -1. And that's because -1 is the same thing as -1 to the 505, because 505 is an odd number. We don't need to worry about the 1 to the 1504 because that's clearly equal to 1. But let's notice that that's the same thing as x1 times x2 times x2 times x3 all the way up to x 2009 x1. But now let's reassociate and recommute this, and we'll see that we get exactly the product x1 up to x 2009 squared, which is clearly equal to 1. Because the product is most definitely plus or minus 1. You take its square, you get 1. But that's an immediate contradiction because we have -1 equals 1. So we've contradicted the existence of such a finite sequence in the first place. Okay, so now let's get to the next problem. And for our next problem, our goal is to find all natural numbers, we'll call them n, such that this quotient is also a natural number. So we've got n cubed plus 3 divided by n squared plus 7. Okay, so maybe we'll start this off by doing polynomial long division. That's kind of motivated by the fact that the degree of the numerator is larger than the degree of the denominator. So we'll take this n squared plus 7 and divide it into n cubed plus 3. So let's see, to achieve an n cubed, multiplying an n squared, we need n. So that's going to give us n cubed plus 7n. Now we will group and subtract. So we group these and subtract them from the above line. That gives us minus 7n plus 3 as the remainder. But since our divider is a quadratic polynomial, and this is a linear polynomial, that means we're done. And now this calculation allows us to write n cubed plus 3 over n squared plus 7 equals n minus 7n minus 3 over n squared plus 7, where I've changed the sign on this just to make it look a little bit nicer. But now let's notice that this object right here, which is the object in question, is a natural number if and only if this object right here is an integer. Why is it an integer and not a natural number? Well, the integer restriction will loosen it up a little bit, and this minus sign kind of takes into account the fact that it could be negative. And anyway, all of this follows from the fact that this number n here is most definitely a natural number to start with, because that's our assumption. So we've changed our question to deciding when 7n minus 3 over n squared plus 7 is an integer. So we can get some immediate simplification here by noticing that this numerator, and thus the entire fraction, is never equal to 0. Well, it's never equal to 0 over the natural numbers, at least, because if it were, then 3 over 7 would be a natural number, which it is not. But if we require this fraction to be an integer, but not equal to 0, that gives us the following absolute value inequality. We have the absolute value of 7n minus 3 over n squared plus 7 must be bigger than or equal to 1. So can't be equal to 0, must be an integer. That means it has to be plus minus 1, plus minus 2, plus minus 3, so on and so forth. In the end, its absolute value has to be bigger than or equal to 1. But now that can spread out into two inequalities. The first inequality would be 7n minus 3 over n squared plus 7 is bigger than or equal to 1. And the second inequality would be 7n minus 3 over n squared plus 7 is less than or equal to negative 1. Just by the strategy for solving compound inequalities based off of absolute values. Okay, but now this guy right here is equivalent to 7n minus 3 being bigger than or equal to n squared plus 7. And then this guy down here is equivalent to something similar. Let's see what it would be. Maybe we could multiply both sides by a minus 1. That'll change this order as well as change all of those signs. So here we have 3 minus 7n is bigger than or equal to n squared plus 7. So let's bring these two inequalities to the top, and then we'll finish it off. So on the last board, we determined that any n that made this quotient a natural number must satisfy one of these inequalities. So we have 7n minus 3 is bigger than or equal to n squared plus 7, or 3 minus 7n is bigger than or equal to n squared plus 7. Now let's play around a little bit with this second one first, because it kind of finishes off more quickly. Let's move everything over so that we're just looking at a quadratic term. So that means we'll have 0 on this side must be bigger than or equal to n squared plus 7n plus 4. But let's recall that n is a natural number, so this is in fact impossible. That's because if n is a natural number, this is at least 12. But 12 is most definitely not less than or equal to 0. So we can't go much further here. So nothing happens over here, which means this inequality must be satisfied. Okay, so let's work on that a little bit. So we'll have 0 is bigger than or equal to n squared minus 7n plus 10. But let's think about what that looks like. That looks like some sort of quadratic polynomial. Maybe looks something like this. So it's upward facing. So we're looking for its two intercepts, and the possible n values will be between those two intercepts. But let's notice that this thing factors pretty easily. This is equal to n minus 5 times n minus 2. So that means that these two values here are 2 and 5. So if we want this quadratic term to be less than 0, we know that n must be in the interval from 2 to 5, but since it's a natural number, it can only be 2, 3, 4, or 5. And now we just have to check each of those one at a time. So let's check maybe n equals 2 right here. So we'll throw that into the original object. So let's see, if n is equal to 2, we have 8 plus 3, that's 11 over, well, let's see, that's going to be 4 plus 7, which is 11, which equals 1. So that means that n equals 2 works. And now let's move on to n equals 3 and see if that works as well. So if we plug n equals 3 here, we'll get 27 plus 3, which is 30, over 9 plus 7, which is 16. Well, that is not a natural number, so this does not work. Okay, good. And now I think you can probably see where you go from here. You'll just want to try n equals 4 and n equals 5. So let's reiterate that we've determined that n equals 2 works, n equals 3 does not work. And we'll leave n equals 4 and n equals 5 as a little bit of a homework exercise. And that's a good place to stop.